Hello and welcome to today's daily Leetcode challenge. Today I'll be going through the answer, going through my thoughts, and then comparing my solution with solutions of others to see where I could potentially improve it. With that, let's begin question 239, sliding window maximum. You're given an array of integers, nums, where a sliding window of size k, which is moving from the very left of the array to the very right. You can only see k numbers in the window. Each time sliding window moves right by one position. Return the maximum sliding window. In my own words, I have a window which is always a portion of the array, a contiguous portion of the array, and that window is sliding. Each time it slides, there is a maximum number within that window. I have to pick it out. Let's look at the example. In an input array 1, 3, -1, -3, 5, 3, 6, 7, and a sliding window of 10, the output would be 3, 3, 5, 5, 6, 7. So let's see. Does that mean that the sliding window does first encapsulate the first three numbers, then the next three, and so on until it reaches 3, 6, 7. Each time it encapsulates three numbers, there is a maximum number within it. So within this subarray, the max number is 3. Within this, it's also 3. Within this, it's 5. And so on until we get 5, 6, 7. All right. Well, so how do I think through this? I would think that I would need some sort of data structure representing this sliding window. And this data structure could be of any size, right? It could be half the size of the input array. It could be length of 1. It could be the whole array, probably. Let's look at the constraints. Yeah, exactly. It could be from 1 to the length of the array itself. So my job, I guess, is to pick out what sort of data structure has the capabilities of being updated almost n number of times. So, and also have search, insert, and remove operations be probably of log n or something like that. And let's see, heap or min heap has the properties of almost all of those. I can say for sure that it has O log n insertion and O log n removal of the minimum value of the array, but what it does not have is a removal of some version of the, or some element of the element in that heap with an O log n. So min heap doesn't, or max heap actually in this case, wouldn't work. Well, there is another sort of, there's a take on an array actually that could satisfy us with this, that could give us the thing that we need here. This is the version of, I'm going to walk through, let's have these steps here, and I'm going to kind of hopefully show you something interesting. What if we were to imagine a queue, a monotonic queue and a queue is just an array in this case. And monotonic means that it is always, it has some sort of property going through it, or consistent through the queue from start to finish. So the property that I propose of this queue is that the numbers in the queue from start to finish are always going to be descending, meaning that the number at the beginning of the array is going to be the biggest, and the number at the end of the array is going to be the smallest. And so how would that look like here? I'm not going to actually be rearranging anything in the queue, but what I am going to be doing is making sure that if there's some sort of inconsistency, whereas like, let's pretend that this -1 is actually of length 5, I would just make sure that this element is the first element in an array, and then since there's nothing following it, then the array would just be of length 1. So what I'm proposing is a monotonic array with a property that it is always descending, and how I'm going to build that monotonic array is any single value in this input array that does not qualify or does not make that property consistent, I'm going to remove it, with the condition that I'm also going to prioritize the maximum number in this array. How is that going to happen? Well, it took us a while to build this, right? We didn't start just from 1, 2, 3, -1. We're going to start with an empty array. And with an empty array, the first step I'm going to do is I'm going to add 1 to it. This is the first time my loop encountered a number. The second time I encountered, I should have planned this more, but I have a 1. The next time I encounter a number, it's going to be 3, right? So 1, 1, and then I'm looking at 3. 3 is going to be larger than 1, so 3 is now going to replace 1, and it's going to prioritize, it's going to keep that, it's going to still keep that property of the array consistent. Next step, I'm looking now at 1, 2, 3. 1, 3, and -1. I have my 3 as my beginning, and I have -1 as my next one. So now I have all of a sudden a array where the largest number in this sliding window is my first element. And also, I'm also only able to do that because I've stayed consistent with my rule that this queue has to be monotonically decreasing. Let's see what the next array is going to be. 3, -1, -3. I've considered this new number, -3, and it still fits my description. And so if you can see, the number at this beginning of the array is still 3. Let's see now, what is my next step? -1, -3, 5. So I'm actually considering the number 5. And since I've actually 3 has now stepped out of the range of the window, and I know the index of it, I can simply just remove it. So I would now be working with -1 -3, and 5. And we see that 5, if I was to add 5 here, it would actually override 1, -1, and -3 because, again, of my rule where the array has to be consistently monotonically decreasing and the numbers around it cannot change, or the indices in it can't change. Then I'm considering, again, the number 3. 3 does fit my rule of being monotonically decreasing. Now I'm considering the number 6. The number 6 is 5, 3, 6, but 6 overrides 3 and 5. Now I'm considering number 7. So my array is 6, 7, but 7 overrides 6, and so I get a 7. And would you look at that? 3, 3, 5, 5, 6, 7. So there we go. That's my answer. I'm going to leave this here as an example for now. But as you can see, as you can see, this keeping up with this structure of a monotonically decreasing array with the condition that it's also doesn't reorganize the order of the numbers in it, and it prioritizes the biggest number, I can safely get this result. So how do I do that, right? How do I in O1 essentially find out which number is the biggest in the sliding window? Well, it's always at the 0th index, but then how do I build it? So what we'd actually need is something called a DQ, or a linked list, where the 0 element is the beginning and the last element is length of the array -1, and with some additional functionality that I need to be able to remove elements from the left and from the right. So that's called a DQ. And let's have a result. And what I'm going to do now is just have a loop where I iterate over each and every element in this array and build my monotonic queue. Right, nums. What I do have to do here is have a bunch of conditions at which I have to have a bunch of conditional statements that indicate when I'm able to actually start considering my window full, when I have to remove an element from the array because it's now out of the scope, and stuff like that. So the first thing that I'm going to do is implement a while loop inside of my for loop that's going to take care of the building of this monotonic queue. And how that's going to look is while queue. So while queue is non-empty, and the new number n that I'm considering is larger than nums. And I'm going to be actually in my queue, instead of the numbers themselves, I'm going to be storing indices of those numbers, because it's going to help me later figure out if my number might have gotten out of range, or the window slid so much that it's gone, or when. Makes sense. Q. Actually, let me monotonic. Q with monotonic peak. Same Q with indices of the window, with indices of the values in the sliding window. There we go. So while nums, and I can say -1, I'm going to say Q pop element. What does that actually do? Well, remember when this element was, I think, was 5, 3, and I appended a 6 to it? Pretend that this is now my 6, and my Q is 5, 3. And what I'm saying is, while the Q is full, and while n, which is 6, is greater than 3, and then later 5, I pop the rightmost element. So I pop 3, then I pop 5, my Q becomes empty. And now that my Q becomes empty, that's it. I now end up with a 6. So after I make sure that my Q is going to adhere to the monoticity and it being decreasing, I'm going to say Q append Q append I. I'm going to append that new index representing my 6th element. Now I simply just have to clean up some of this lingering states. Well, first of all, I need to be able to figure out when I'm starting to consider elements of my Q for my result. Now the reason is because if you notice, prior to this, I had 2 more arrays here that were partially populated, because I started off with populating it with 1, then with 3. Here I would also have to say that. So if I is less than k minus 1, I'm actually going to, no, let's say bigger than k minus 1. So if so it's k here. K is 3, and my I here is going to be 2. So if it's greater than or equal to k minus 1, then I'm starting to consider Q as being a valid window. And I say result append, and I'm going to append what to it? I'm going to append nums Q of 0. Oops, Q of 0. And finally, now that I've added it to the result output, I also have to clean up the window from any indices that are now being slid away from. And how I would do that is if Q of 0 happens to be less than I minus k. So let's say that we are here, right? And this element is 0 of index 0, and I'm moving to the next element, which is now going to be 0, 1, 2. Oh, 0, 1, 2, and 2 minus k, 2, minus, I is 2, is plus 1. Then I have to say Q pop left, return res. So if my index is now at this is 2. 2 minus 3 is -1. Plus 1 is going to be 0. So yeah, there we go. If my index runs out of the range, or someone made that mistake. Then pop it from the queue. Pretty sure that was collections. I would have to look it up. Collections DQ. I spelled DQ wrong. So many mistakes. Nums. My apologies. Okay, something went wrong. Seems like because that's not what I want. I don't want nums of 0. I want nums q of 0. I remember accidentally deleting that. There we go. So let's go through this once again. Just keep in mind that this queue that I'm working with has these properties. It is a subset, a contiguous subset of some of the numbers within some of the indices within my sliding window. It is monotonically decreasing. And since I have that, this is my element to build my monotonic decreasing queue. This is the portion to append to it, meaning to actually still just build it, just with the upmost index. This is to append the result in the case where my window is actually built. And this final is another cleanup mechanism to the monotonic queue when the window slides out of its range. Let's submit it. I think this is pretty intuitive and so it works. Great. All right. And it seems like I've done this in a while ago. Maybe I can compare it to my own solution. Yeah, pretty hard to read, but my solution was 5%, and now it's in the 95th percentile. Okay, but Java's good though. Okay, let's quickly compare our most up-to-date solution with some of the possibly better solutions here. Okay, I'm assuming they're also going to be using this sliding window approach. These are just some edge elements or some edge conditions, edge cases. Also another edge case. So if k is equal to 1, then return nums. If k is the length of the array, then also return it. Answer DQ for I in range. So here for I in range k, while q, here they build the array or build the queue. And here they go through the rest of the array with already a pre-built queue. Okay, so this is the same exact solution with some other nuances. Like for example, these edge cases, which we can just copy and paste into our solution. And here they're pre-building the array, which makes it less harder to read, but definitely maybe a little bit faster. Let's see how much this increases our speed. Not significantly, but even a little bit slower. Okay, well, with that, I would say that this is probably way cleaner than things that you see in the solutions with a higher or less runtime, but again, cleaner is always better, easier to understand. Okay, well, with that, thank you for watching, and I'll see you in the next video. Bye.